There are two main approaches when doing research or analysis. You can start with data or you can start with a hypothesis. Both approaches can work well for your particular problem as long as you are aware of their potential limitations.
And the big question is, can we put the data before the hypothesis? In the bonus material you can read a lot more about different statistical techniques to use to get started with people analytics. And we'll give you plenty resources to do that. But in this lesson we're going to focus more on the theory behind the statistics. And that's important because in HR we work with a big volume of data. And when you work with large quantities of data, you can do certain techniques called explanatory data analysis, which basically is the concept of throwing a whole bunch of variables in one, for example, correlation matrix, and just checking what are the interesting effects, significant effects that I see in my data, and can there be a useful story behind that data? Now that approach is opposed to normal quantitative hypothesis testing, what we did in the previous two videos, because we started with a specific question, with a hypothesis, and we tried to falsify it. We couldn't falsify it, so we confirmed it and we found an actual effect. This lesson is about this very specific topic. And that's important because with techniques like deep learning, machine learning, we can learn a lot about big quantities of data and we don't necessarily need a hypothesis. So this lesson is all about statistics. We're not going to talk about the normal distribution, neither are we going to talk about the paranormal distribution. You can read more about the normal distribution in the bonus material for this week. We'll give you a link to a lot of very useful resources. Now, one important thing to point out is that in statistics, 100% evidence is an oxymoron. And why? Because in statistics we work with probabilities. We work with p-values, and p stands for probability. And a p-value of 0.05 means that the probability that the statistically significant effect that you find is coincidental is 5%. So the probability is 5%. And at the 5% point you think like, hey, if I expected a certain effect and I have a 5% chance of probability, that's quite a slim chance, so it's probably a statistically significant thing and a significant relation between the two variables that I'm studying. That's the idea of the probability factor. So 100% evidence is impossible to achieve in statistics. And that's for example also why you see in medicine a p-value of 100 or 1,000 or even a 10,000th, because you really don't want to have a lot of medicines out there that have a relatively high probability of failing and of not having the effect that you actually thought you found. Because if the active ingredients of medicine go wrong, you actually have a problem. And that's why they go to values of 1,000th, for example. So what you see is that a sample never fully represents the full population. For example, your engagement survey has a response rate of 80%, which is really good, but you're still missing 20%. And it's the same for your data. You try to clean your data, you try to make your data as crisp as possible, but you always miss data. You miss a department, you miss a few people, and your sample is never fully representative of your full population, your full working population. And in addition, your population changes, people join, people leave your company. So your analysis tries to touch on reality, but it's never reality. Secondly, most models are based on assumptions. And you saw this when we were doing the regression analysis. From literature, we knew that there's a relationship between engagement and performance. So we did a regression analysis and we said, hey, if there's an effect, we assume that engagement leads to performance. So there's a big assumption in the model, and based on that assumption we also choose a specific model. But there's way more assumptions in your statistics. For example, you have the assumption that your data is normally distributed, which is a prerequisite to do a regression analysis. And there's lots more assumptions when you dive deeper into the statistics. You can never be sure that all those assumptions are perfectly correct. So once again, 100% evidence is impossible to reach. And all analyses have false positive and false negative probabilities. And that's when we end up with a confusion matrix. And when you predict a certain outcome, and your prediction is positive, so you expect a statistically significant result, and it is a statistically significant result, and the actual value, the real value, is also positive, you have a true positive. But when you predict an outcome and you say, hey, my statistical analysis shows that there's a statistically significant positive relationship, but in actuality there's a negative relationship, you have found a false positive. So you think it's true, it's positive, but it's actually false. It's a false positive. And the other way around, you can also have a false negative and you can have a true negative. In the ideal world, you only find true positives or true negatives, because then the outcome you predicted is actually representative of reality, the deeper real meaning behind the analysis. But you really want to limit the number of false positives and the number of false negatives. And when I just talked about, for example, medicine testing, statistical testing on active ingredients in medicines, you really want to lower your false positives. So you really don't want to think like, hey, there's actually a relationship between them, when there's no relationship between two active ingredients in a medicine. So you really don't want to have false positives, you only want true positives. So that's when they move the probability factor from 0.05 to 0.001, for example. That's just to really limit the number of false positives in this case. So this is something to always keep in mind. When you do your research, when you do your analysis, there's always a chance that you find an effect that's not there, or that you don't find an effect that is actually there. Now, what we said previously, and now I'm going to confuse you, is when you start doing statistical analysis, you start by looking at literature. And you create a model by looking at what literature says. And when I say model, I mean you have an independent variable or multiple independent variable. You have a number of control variables and dependent variable, like we saw at the start of this module. And by having that model, you do your statistical analysis and you try to confirm your hypothesis. And the actual way to do this is based on Karl Popper's theory of falsification. What you do is you have a certain hypothesis, you try to disprove your hypothesis by saying, hey, can I actually find out that what I'm thinking is not right? And if you can't find it out, so you really struggle to falsify it, and if you can't falsify it, then you can assume that your hypothesis is correct. But again, you can assume it because you can never really prove it. But there's something called the confirmation bias. And the confirmation bias is a phenomenon in which you really try to find the effect that you were looking for. So for example, when you think engagement leads to performance, and in your analysis you don't find that relationship, you start, for example, to think like, hey, did I include the right control variables? Maybe I should add department, or I should remove age, or I should remove gender, because then I will actually find a statistically significant effect. So the confirmation bias is risky in statistics because you always have the ability to work and play with the data and to redesign your data in a way that helps you to find a statistically significant effect. And that's what you see a lot of students do when they try to graduate. But that also often happens in social science. And the crisis that psychology, especially psychology and social science, is in at the moment, what they call the reproducibility crisis, where they took 100 prominent studies and a big part of those studies they really couldn't replicate, has to do with what I just told you. In order to prevent this, we start with a question and a predefined data model, and we try to fit this model on the data that we have, and we already thought about that, of course. And if that doesn't work, we say, hey, we're not going to tweak too much with the data, because at that point we run the risk of falling into the confirmation bias. And we try to find a statistically significant result. That's a traditional approach of data. But nowadays we have a lot of data. So a different approach is looking at the patterns in the data and using those patterns to formulate hypotheses. And there's a number of golden rules for this. First of all, when you're working with mature areas, for example, your recruitment, the predictors of performance, predictors of turnover, you try to use existing theory to build your models. So what I did with the regression analysis, we know for years already that engagement and performance is linked. We don't necessarily know too much about the relationship, whether engagement leads to performance or the other way around. It's often a two-way relationship, But we know that the two are directly and closely linked. So we don't necessarily need an elaborate research design. But when we start working with less mature areas, for example, social network analysis, the number of contacts, is that indicative of someone's performance, for example, or the impact of flexible working hours, that's a new field of research or a new sub-area of research. You want to focus on more solid research designs, and a really, really good tip is to partner up with academia. When I talk about solid research designs, think of longitudinal studies where you take multiple measures over time and where you try to find cause and effect relationships by really having a solid research design. And the second tip, to partner up with academia, is really, really beneficial in this, because on the one hand, it helps you to learn. It brings in a knowledge partner with a lot of very, very specific, area-specific knowledge. And it's a partner that's really, really happy to help you, because you can provide them data, and they can use that data for their own purpose, and they can help you with it. So academia is actually a really, really good partner in this process. But always keep in mind that 5 out of 100 correlations are significant by chance when you test with a 0.05 p-value, probability value. So, for example, when you try to relate performance to someone's favorite ice cream and say, hey, is ice cream indicative of someone's performance? And you test 100 different flavors, you'll probably find 5 flavors which are correlated with superior performance in your high-performing individuals. But most likely those flavors, those relationships are significant by chance. So when you think about this example, you understand the risk of testing too much. Because if you test too much, you'll end up focusing on those 5 out of 100 significant relationships that are significant by chance. But you don't know that they are significant by chance. You see a number of significant relationships, you forget all the insignificant ones, and you start focusing on them. And maybe you'll make wrong decisions based on those statistically significant relationships. And that's really a risk. And that's something you always need to watch out for and always be conscious of. So don't test your data too much, because you run the risk of the confirmation bias and you run the chance of finding statistically significant random effects. Now there's a different approach, and that's your take home. Until now, we've mostly talked about the confirmatory data analysis. You have an hypothesis and you actively try to confirm it by actively trying to falsify your hypothesis. That's the idea of the confirmatory data analysis. However, you also have the exploratory data analysis, and that's what I mentioned at the start. You can throw all your data in one big correlation matrix and say, hey, which data points correlate with each other? And some of them will light up, and you can use that data to suggest new hypotheses to test. So when you say, hey, my performance data is randomly connected with the number of emails that someone sends, what does that mean? And what does that mean for the specific job that a group of people have? So using the data, you can come up with suggestions of new hypotheses to test. So what you do is you explore the data, and based on that explanatory data analysis, you formulate the hypothesis that could lead to new data collection and new experiments, and in the end, new insights. In the next few years, you'll most likely see the frequency of the exploratory data analysis increase. It will happen more and more and more often, especially with increasingly sophisticated machine learning algorithms that do analyses for you. So they throw all the data on one big pile and they try to come up with interesting effects. At some point you will come across it, if you haven't already, and you'll start to work with it. And the important thing is to find the balance. Because the hypothesis testing is important, and that's a well-established field of study. Now, the exploratory data analysis is more recent, and from the top of my head, it was 1987 when John Tukey, the brilliant statistician, published about it in one of his books. The important thing is to find the balance between, on the one hand, the hypothesis testing, the traditional hypothesis testing, and on the other hand, the throwing all the data on one pile and coming up with interesting relationships and new insights in your data. It's important to keep the balance between both approaches, but in the near future I see the exploratory data analysis being used more and more. But be careful, because when you have a correlation analysis and you try to correlate 20 or 30 factors with each other, you'll end up with around, well, my math skills aren't that good actually. I'm a better statistician than a mathematician. But you end up with, I think, around, well, when it's 20 times 20, you'll end up with around 200 or 180 unique correlation values, and around 5% will be by chance. So you end up with almost 9 or 10 statistically significant values that are significant by chance. So that's the big risk of the exploratory data analysis. However, it does enable you to efficiently start with the data and come up with very specific hypotheses for subgroups, for example, in your population. So keep that in mind when you ever start to work with exploratory data analysis, and a lot of the systems that throw all your data together and then try to build stories on top of your data use this explanatory approach. And it has a lot of advantages, but as I said, it also has disadvantages. So to wrap up, in mature analytics, both approaches are needed. On the one hand, to confirm mature areas of research and apply it to your specific organization, and on the other hand, to find very specific and unique effects that you wouldn't have found using the conventional means. But then again, two final points. Be aware of analysis paralysis. In the material for this week, I'll link to an article written by David Creelman about analysis paralysis. And one of the big risks is that you focus too much on data that's not really relevant and that you really can't act on. And that's not good, because then you run the risk of becoming paralyzed by all the analysis or all the non-relevant analyses that you do. Keep that in mind. Focus on the things that add value and that are actionable. And second, the thing we've talked about in every single module, keep business relevance in mind. Also, when you do exploratory data analysis, you'll find a lot of interesting effects, but always ask, how relevant is this for the business? And that also has to do with actionability, but it also has to do with the relevance. Am I focusing on a group of key employees that really add value to my business? Or am I focusing on a smaller group of employees that are not really vital for my business? And am I focusing on small effects that really are interesting from an academic standpoint, but really don't add that much value to practice and to the rest of the organization and to the rest of the business? That's something to really focus on and to keep in the back of your mind. Anyway, I created this lesson because I read a discussion that was started by Max Bloomberg. And I read this discussion, and a number of people contributed, a number of brilliant people in the people analytics space. And I thought, this is just too perfect, because it's a high level. You need to have a solid understanding of statistics to really understand all the different elements that I mentioned in this video. But when you do, or when you just get the basic grasp of it, I can say congratulations, because then you know what you're doing, and you don't necessarily need to be a data scientist to understand this. Because oftentimes you're not the person who's doing the data analysis, but having this knowledge is really, really important, because it helps you to prevent a number of risks from happening, and it helps you to prevent falling in certain traps that you really, really don't want to fall in. And bottom line is, you know what you're doing. It's deep stuff that we just talked about. Don't be scared when you don't understand everything. But I hope you understand the main message. There's multiple ways of approaching data, and the bottom line is, whichever approach you seek, and you'll probably take a balance between the two different approaches, you'll probably use them both. But there's advantages and there's disadvantages in all of them. And in the end, 100% evidence doesn't exist in statistics. Because in statistics we work with probabilities, and probabilities are not 100%. Anyway, that was a lot of information. I really, really like making this specific lesson because it really, really touches on the essence of using statistics to come up with new ideas, to come up with new effects that have never been found before. And if you can do that, you're doing really amazing stuff, and you're actually advancing the limits of science and practical application of science. And I think that's one of the greatest things that we're actually doing right now in people analytics. So to answer the question, should we put the data before the hypothesis? Sometimes we should, and sometimes we shouldn't.